in the back? Fantastic. So I apologize, I'm still very sick. So if I wander off or trail off, just let me know. This is, I think, the last talk of the day. So we can play this a little bit more loosely. So if you guys have any questions, just shout them out. This is actually a fairly long talk that goes at a pretty fast clip. It's about an hour long. But if you have any questions, I'm sure they won't mind too much if we run over a little bit. The title of this talk is Embeddings of Python. I kind of want to show you about Python as a C application in the context of how you can embed it in other C or C++ applications. But before I start, I'm going to go through the standard introductions. So this is the 5th talk I've given at PyTexas. So most likely I've run into some of you before, or all of you before. But just to belabor the point, I'll reintroduce myself. My name is James Powell. I'm here representing the New York City Python meetup group. Once this page loads, we can see that there we go. This is the New York City Python meetup group. It is one of the largest meetup groups in the world. I like to show people the meetup.com webpage and all the Python groups in the world. And if you scroll down, you can see that among the top 10, we are number 6. And among those that are specific to Python, we are number 2 after the Boston meetup group. This is something that we're very proud of in New York. We have an enormous number of events. We usually have 2 or 3 events every week. We have a large talk event for 100 or 125 people 2 times a month. There is an enormous amount of energy and excitement around Python in industry, in academia, in research, or in web programming, and just for fun in New York City. So if any of y'all are able to make it up to the city, please look us up. I'd be happy to show you around. You can see this is me right here. One thing that I didn't show is that we gave everybody titles on the meetup group. So I started to call myself the head honcho, the big cheese. And one of the members of the group is writing a script to swap out which cheese I am on some schedule from the cheese shop skit, the Monty Python cheese shop skit. So for the time being, I am the big cheese Kraft Singles. It goes well on, it's the only cheese for a grilled cheese that's acceptable, so I'm not too upset. This talk is given as, there really aren't slides for this talk. I want to show you a lot of real code, so it's a live coding talk. I do have a little bit of notes in an IPython notebook. One thing that I'd like to tell you guys about is a Python distribution called Anaconda that makes installing Python libraries very, very easy. Or to put it another way, if you were to run one of these IPython notebooks and it used matplotlib or it used numba or numpy or scipy, you may find that it's very difficult to get these tools installed. There are a lot of dependencies, and depending on your platform, it can be a little bit difficult to actually get it up and running. I really heavily recommend that you guys use Anaconda in this situation. It is incredibly useful, and it comes with almost every library that you'll actually need for playing around with Python. I'm also going to pitch my blog, seriously.don'tusethiscode.com. I plan to, within the next few weeks, post all of the notes for the talks that I've given at PyTexas, as well as a little bit of additional information that I run across, and just a couple of side notes and errata. I haven't posted in a while, but it's something that I really plan to get back into. I also have to say that, this domain name is so awesome, seriously.don'tusethiscode.com. So, I got to put it to use. So, let's get started. Each one of the talks that I've given at PyTexas centered around a set of themes. And the themes are very similar between the different talks, but I want to talk very briefly about the themes of this talk. The broad themes are, and the real takeaway is kind of looking at CPython, the C code behind the interpreter, as a source for understanding. This is a tool that you can use in order to better understand the language and to get a lot of depth in the language. I think also that as Python programmers, we sometimes find ourselves a little bit intimidated by code that isn't written in Python. We may find ourselves intimidated by code that runs the interpreter. And one thing that I would like you to get out of this is that the C Python interpreter is incredibly easy to read and reason about. This is a very, very useful resource for you guys, in developing some expertise around different areas of the language. Additionally, I'd like to stress again this view of Python as a system within a system. This is an attitude that I think was lost in the last 20 years. The old Unix hackers really didn't see that much of a distinction between code written in one language and code running in another language. They didn't see that much of a distinction between, awk scripts that they wrote and the awk program itself. And for them, it seems very natural that, Python is just an interpreter running on top of an operating system with user code written in terms of some domain-specific language. They didn't really see such a stark distinction between these three layers. And I think that we can adopt that same attitude to great benefit. Additionally, this talk shows you some very speculative things that I think are actually kind of fun. So the order I want to go in is, you can see this is actually a very structured talk. And the order I want to go in is I first want to show you guys just one of the common examples we're going to be using throughout the talk. Every element of this talk centers around one specific example that I was inspired to use by a talk I heard about PyPy and by a very controversial statement made in that talk that Python cannot be compiled. I'd like to show you just the Python source code. You can download it from python.org very easily. I want to show you compiling it under GDB and how you can use GDB to debug the Python interpreter itself. Then I'm going to show you the very high-level embedding. This is one of the embeddings in the standard documentation. I'll show you the pure embedding, which is another embedding in the standard documentation. I'll show you extension modules, which is something that you all are using already as part of the standard library. And then we'll start to look at some very speculative, very interesting things. We'll start with a Cython module and then look at what I call a zero interpreter embedding or a medium level embedding. And then we'll get to the really cool thing, which is the Python 3 running within Python 2, which is really weird, wild stuff. That's my David Letterman for all you guys. So just to start, I'd like to specify that this talk is given centered around Python 2. IPython notebook here is running 2.7.3. The source code that we'll be looking at will be 2.7.5. The differences between the two of them for the purpose of this talk will be very minimal. I'd also like to make sure that you're familiar that in the sys module there is this version info that can tell you information about the version that's currently running. We'll make use of this later. And also in the OS module there's a function called getPID, which gets the process ID. And we'll also make use of this later. So the common example that will be used throughout this talk is a little bit abstract, but it's just a function, f, that takes 4 parameters, 2 types and 2 values. And what it does is it constructs a value using the first type and the first value, and the second type and the second value. So I'll show you it in use. If I call it with int 10, then I create an int with the value of 10, another int with the value of 10, and I multiply them. And I get 100. If I just change this int here to a string, then I get a string with the contents 10 multiplied 10 times, which will result in concatenating the string 10 times over. So if this were the letter A instead, you can see, get attribute name must be string. Oh, because I have to execute these in order. There we go. And you can see it just duplicates the string 10 times over. Now, one thing that I want to do is some of the examples that we'll be looking at are examples that are supposed to be run from the command line. And so we don't have the ability to just use these built-ins in this form. So the only one modification to what we'll actually be using is that I'm going to do this additional step where I pass everything as a string, and I just pull it out of built-ins. So you can see this is the same as the first function, but I've just passed every parameter in as a string. And I'm just, if I pass an int, I pull int by getAttr out of built-ins. If I pass an int here, I'll put int out of built-ins using getAttr. And so with the same 2 examples above, you can see we get these expected results. So the first thing we're going to look at is Python source code. So here is my terminal, and let's bounce that up to granny size. And we'll go into a directory. So I have everything laid out for us to look at. This directory is a directory containing the source code for Python 2.7.5. And if you scan through this, you can see it's pretty easy to figure out where everything's going to be. Python contains information about, or contains source files around the interpreter itself. Objects contain source files that are used for some of the standard objects, dictionaries. You can see float object, func object. The dictionary object is in here as well. Modules contain some standard modules in the standard library that are written in C. So you should be able to see POSIX modules written in C. itertools is in here, I think somewhere. No, itertools is in another place. And if you look in lib, you can see a lot of the standard library here. So it's all pretty straightforward to look through. The first thing I'm going to do is I'm going to compile this. And I'm going to compile this with some debugging flags. And I have this stored already. So let me look for PyDebug. And this is my standard way to compile flags. Oh, PyDebug. To compile Python. Now, I'm going to do this talk in the form of like a cooking show where I'll show you what I'm going to do, but I'm not actually going to do it. I'm just going to put the uncooked thing on the shelf and then pull out of the shelf what my assistants have made 2 months ago. The only thing I really want to show you is that when you compile Python, there's one really useful thing that you can do. You can pass it some C flags, G3, GGDB, and GDOR4. It will make the process of debugging Python incredibly easy. So let's assume that I've compiled this and I've built it. And you can see that I built it in a directory that's the same as the present working directory with a dash build. This is just a convention that I use. So let's run Python under GDB. Python. So we have GDB loaded up, and we're going to run. Oh, we got to get this going. And it's build bin Python. And we run it. And here we have a standard Python interpreter. Nothing too fancy about it. This is a debug build of Python. So you can see that after every line, it's printing out the number of reference counts. This is just a tool that's used for assisting in memory debugging. And it adds a little bit of noise to the screen. I probably should suppress this next time. Now, the next thing I want to show you is how we can use this to understand a little bit more about how Python runs. So I'm going to take this example, this function where I multiply two things together, and I'm going to put a breakpoint. I'm first going to disassemble it, and I'm going to find the name of a bytecode. I'm going to search for a bytecode in the main interpreter loop. Then we're going to set a breakpoint there, and we're going to see some interesting things about what happens behind the scenes. So here's a simple function that just returns x times y. There's nothing magical or interesting about this function. And if I call it with two arguments, 10 and 20, I get 200. If I call it with a string, ASDF times 20, I get ASDF repeated 20 times. Nothing interesting, nothing magical here. If I use dis from the dis module, and I disassemble this function, I get the bytecode for it. And this bytecode tells me exactly what this function does. It loads x and y onto the stack, it multiplies them, and it returns it. Fairly simple, exactly what we'd expect it to do. This binary multiply is the name of the bytecode that actually does the multiplication. So let's look at what that looks like in the source code itself. So I can tell you that we could, if we didn't know where to start looking, we could just grep for it, and we'll see one place stand out, Python ceval. So Python ceval is where we'd look. And if we search in this file for binary multiply, we can see that this is actually the code that runs when we do a multiplication. This is what code runs behind the scenes. And you can see that this code's fairly easy to read. It pops the two arguments off the top of the stack, and it multiplies them. It decrements the reference counts, and it sets the result to the top of the stack, and then it's done. It checks for an error value here, but otherwise, that's all it does. And if we look at PyNumber multiply, we can see PyNumber multiply does a little bit of dispatch based on the type. So if this is a sequence method, it'll do something, it'll actually do the repetition. So if it's a string, it'll actually do the repetition as opposed to the actual raw multiply. If you dig into what binary op1 does, you'll see that it's pretty hairy. And it goes through a lot of steps trying to determine if these happen to be custom objects, which underscore add or which underscore mul it calls, and so forth and so on. Let's try debugging this. So we can see in my Vim session that binary multiply starts on line 1261. So what I'm going to do in my debugger is I'm going to break out of Python, and I'm going to set a temporary breakpoint in ceval.c 1261. Nothing too special. Then I'm going to run again. Actually, I'm going to continue. And then I'm going to call my function one more time. And when I call my function, that debug, that breakpoint is going to be trapped. And you can see this is exactly what happened. If we look at where we are in the code, we can see we've just trapped at that point. So we know that this binary multiply is actually what's happening behind the scenes. Now, one interesting thing we can do from here, without going any further into the code, is look at a backtrace to see how it is that we got to this point. And that'll reveal to us some very interesting things related to how we can embed Python. So you can see this binary multiply is part of a switch case statement in a function called pyeval frame x. And if we go down the stack, we can see all the different routes that it took. But towards the bottom, we'll see something interesting. This here, modules python.c main, is the main entry point for Python being run from the command line. And we can see that that passes to a function called pymain, which passes to a function called pyrun any file x flags. So let's take a look at pyrun any file x flags. Now, one thing that I've done to make this a little bit easier is I've built a set of tag files. So you can see I can do auto-completion. I can jump around the source code by name very effectively. Oh, I actually want to go to the third choice. So here you go. Pyrun any file x calls pyrun any file x flags. And you can see that in the source code, there are a million different versions of pyrun any ... There are a lot of convenience functions for passing arguments by default and whatnot. This is the actual entry point for Python interpreter. And it's very interesting because you can see things that you'd expect to see. If you're running in interactive mode, it calls pyrun interactive loop flags. And if you're running a script, it calls pyrun simple file x flags with a bunch of arguments like the file name and a lot of flags and a file pointer and whatnot. This is the key to what the documentation calls the very high-level embedding. So the very high-level embedding is what if, instead of entering at that main function, we enter into Python from a larger C application by just calling that function 2 up in the stack, namely pyrun any file, blah, blah, blah. I don't remember all the names. There's actually a million different names based off of which default parameters you want to take and what inputs you want to give it. So I'll show you an example of that in the file Cython embedding. So this is what the very high-level embedding looks like. And it should be something fairly straightforward to understand. My C code is not very good. I haven't written C code in a very long time. But I'll step you through pretty much what it does. I take arguments from the command line. I construct a string using sprintf. And that string is merely the code that I want to execute. And you can see that in this case, it takes the first string and constructs a value with the second string, takes the third string and constructs a value with the fourth string. So this is like int 10, or string 10, int 10. Exact same example we looked at the very beginning. And all I do is I call pyrun simple string. And pyrun simple string is an entry point into the C interpreter that takes a string as input and prints things to the output. You can see that there's no value returned. So my program, my larger C program, has no ability to interact with the results of this. But you can see that I can just kind of go off and run some code from within my C program without shelling out, without leaving, just going into the interpreter using this pyrun command. So let's take a look at this in use. Embedding. So if you want to look at the makefile, I'll show you the makefile very briefly. I created makefiles for all of the pieces of this project, which will be posted with the notes. I won't actually make them right now, just in case something has changed on my system and it doesn't build. But the makefile for this is very simple. The file is embedding.c, and I can use this Python2 config file that comes with my system to help me fill in missing definitions for where the includes are, what libs I need to bind against. I'll show you just very briefly Python2 config libs. Gives me all the, Python2 config libs. Gives me all the libs I need in order to actually build Python. So I need the Python 2.7 lib. I need the DL lib, pthreads, util. And Python config includes gives me the path for all the includes. And this will be dynamically determined based off of how it was installed in my system. So this is one way that I can make a makefile that is actually somewhat portable. So let's assume I've made the file, which I have. And it's been built as embedding. And I'll just try it. 10 times 20 is 20. and the string 10 times the number 20 is 10 repeated 20 times, and a string times a string is some error. Nothing too fancy. This is what's called the very high-level embedding. And this is the simplest and most direct embedding that you can have. So you have some large C or C++ program that you're running, and for some reason you want to go off and run some Python code. And you don't really need to interact with the output of it. You don't need to, there's no control loop where you need to look at the output and then make some decisions. You just need to go off and run some Python code off to the side. Maybe a script or some automation, and all you have to do is use pyrun, simple string, and you're done. Very, very simple. The next level of embedding is what's called the pure embedding. So when we looked at the C interpreter code, when we looked at binary multiply, we saw a couple of operations like PyNumber multiply, like decref. So we pop two things off the top of the stack. We call this PyNumber multiply method. Then we decrement some reference counts. Then we set something. And what we can do is we can take those C functions like PyNumber multiply, and we can write them directly into a C program. And this is what's called in the documentation the pure embedding. So the pure embedding looks something like this. For the exact same program, it looks something like this. So you can see in Python, everything is a PyObject pointer or a reference of some sort. And you can see there's an enormous amount of boilerplate in this program. I create a bunch of PyObjects because I know I'll need them. I have a little bit of, this is actually a more sophisticated program than the last one in that I actually will trigger a warning if you give it the wrong arguments from the command line. And the other one, if you gave it the wrong number of arguments, it would just core dump. And you can see I do some very simple things. I take a C string and I convert it to a Python string using PyString from string. I get the built-in library by doing PyImport. So that's just a C function that's used within the C interpreter to do the importing process. So I import the built-in module. I call PyObject getAddr to actually do the getAddr call. So what I've done is I've looked through enough of this source code. I've looked through the path that it takes to run my code. And I've identified functions that map to these high-level Python functions, and I've just written them directly in C. And you can see that I'm actually interacting with them very directly, in that my C program has a PyObject reference here. And it could swap them around, or it could check them, it could call functions on them. It can interact with them in a way that the very high-level embedding could not. And then you can see I create two tuples. I use CallObject to call the function with the tuple, so I'm calling the type with the value. So if you remember, the signature was type 1, value 1, type 2, value 2. The call of type 1 with value 1 and type 2 with value 2 is just a PyObject call object. And then I do a lot of manual memory management. And then finally, I call PyNumber multiply, and I print it to the standard out. Nothing too fascinating or exciting. But this is, you can see, a very direct interaction with the Python interpreter. So let's take a look at that in use. I'll show you the makefile for that. So the makefile for the pure embedding looks almost identical to the makefile for the, actually it looks identical to the makefile for the very high-level embedding. The only thing that I've added to this is a couple of debugging flags, G, G3, GDB, GDWARF4. I'll say that the reason to add these debugging flags is if you start to really debug the Python interpreter, you'll see that a lot of things are written as macros. And when you build Python, you'll lose that macro information. This GDWARF4 flag actually allows you to retain the macro information. So in the debugger here, I can do info macro. And it does actually tab completion. This is why I like GDB, even though LLDB is a slightly more maybe sophisticated tool. But I can do PyType, I think, is a macro. No, PyType is GC maybe a macro. Yeah, PyType is GC is a macro, and you can see that it actually told me what the macro expanded to because it collected that macro information along. This is an incredibly useful tool that I've had when debugging C code. Andrew? It does. The limitation with LLDB is it doesn't support all of dwarf, so there's no way to export. Currently, there's no way to export macro information. Additionally, there's no tab completion. There's a lot of small missing functions, so GDB tends to be a little bit more convenient. I think the tab completion is really, really nice because I could do info function, PyObject, and I get all the PyObject functions, and I can, because I don't always remember where the underscores are, where the capitalization is. So I prefer GDB just from that it's a mature tool that's had a lot of polishing done. So you can see the makefile for this looks pretty much the same. And if I run it, pure embedding, it actually gives me some usage information. So let's call it with int 10. Int 10 gives me 10 times 10. If I call it with string 10, it gives me 10 times 10 equals that. Same program, but I've now encoded it in a very different way, in a way where my larger application can actually interact with this. Now, before we move on, I want to show you what an extension module looks like in Python. This is something that I think is very useful to understand, because sometimes we have code that, for one reason or the other, we need to make as fast as possible, and readability or maintainability or portability are secondary concerns to performance. So we're willing to sacrifice our code not necessarily running on PyPy. We're willing to sacrifice having to have an extra engineer who knows how to write C to maintain this. We're willing to sacrifice that, for example, if a new Python version comes out and they've changed something under the hoods, we may need to adjust our code to accommodate that change. We're willing to sacrifice that our code may not work with Python 2 or Python 3, because what's most important for this code is optimization. So I'm going to show you two extension modules in the standard library. My favorite module, itertools, and another module, the math module. And I'll show you a module that I wrote for another talk called NYC, just to show you how easy it is to write a module like this. How easy it is to just actually write a Python module in C, where you may have the opportunity to add optimizations that you may not be able to have access to in Python. For example, you could, if you wanted to, take an algorithm and write an assembly version. So you care so little about portability that you don't care if your module doesn't work on another chipset, doesn't work on another processor, doesn't work in another execution environment, because speed is the most important thing for this module. And I think that sometimes we do run into those problems if we're doing video processing or audio processing, or some sort of gene folding, or even financial applications. So let's take a look at itertools. So I'll use itertools, tools module, math module, and NYC. There we go. So this is the itertools module. And we're familiar with things in itertools like T, and we can see that the T object is in here somewhere. The T object's here. All the stuff that we're familiar with from itertools is here, and you can see that at the very bottom of this, they have this init itertools function that is creating a bunch of these different types for the combinations type, drop while, take while, group by, and all the different helpers that we're familiar with using in itertools. The math module is very similar, and the math module is actually just a collection not of Python objects or Python types, but mostly just functions that are written in C that are just bound directly into Python. So it's a very good example for if, for example, you have some C library, you want to write Python bindings, and you want to see how it's done in the standard library, the math module is something they should look into. This is an example of somebody taking a bunch of math functions that are written in C and just getting bindings so that they could interact with the Python interpreter without having to add an object system on top, or without having to restructure how they're used. And if you look at this struct here, this struct defines the methods in the math module, and you can see these are all the things that we're familiar with. Arc cosine, hyperbolic arc cosine. Who has actually ever used hyperbolic arc cosine in a real program? I don't think I've ever actually used it. I think I know what it is, but I think it is a little bit obscure. But clearly somebody's using it if it's in the module. You can see also factorial. I've actually used factorial a couple places. Your gamma function, power, sine, square root, whatnot. And you can see that all that they're doing is they are, let's take a look at sine. Oh, they're actually binding this from another file. So let's see what's in here that we can look at. You can see that in some cases they're, I don't know if we want to look at that, m gamma. You can see that this is the error function, and they've actually written the error function out. And the error function is then bound to, if you scroll through this, you can see how it's bound to the actual Python function. And at the end of this module, they have another init math where they just initialize all of these different pieces so they can interact with the Python interpreter. And so here's NYC. This is one of my most useful helpers. It gets a pairwise view of some iterable. So if you give it a string, it'll get the first letter and the second letter, then the second letter and the third letter, then the third letter and the fourth letter. It lends itself very well to solving a lot of problems. And I wrote it in about 111 lines of just C code, most of which is boilerplate. And just to show you how much of this is boilerplate, pretty much all of this here is boilerplate. All of this here is boilerplate. It's just setting up the object. That's just the init on it. And the real meat of it is all here. It's about 10 lines of meat and about 90 lines of boilerplate. They're having a lot of fun next door. I wish we were having as much fun in here. If anybody wants to cheer or shout out, letters that are Python related, I am totally willing to pause this talk to have as much fun as the cheerleaders next door. But you can see in this case, this module definition looks the exact same. I have an init function at the end, and that's what the interpreter calls to initialize this module when you do the import. And all it's doing is initializing the methods and adding this object NYs that I'm using for doing the pairwise view of my iterable. And I do one nice thing that, if any of you guys are old C programmers, this is something that was introduced, 10 years ago. That's very nice. When you create structs, when you have a literal syntax for defining structs in C, you can actually have a name syntax. So this, just like in Python with keyword arguments, you can actually do the same thing in structs in C now. I thought this was really neat when I went back to C very recently for putting some of this stuff together. And I noticed that you don't have to guess where the fields are by their position. You can actually name the fields. So you can see this type has a field called TP_name, a field called TP_doc, a field called TP_new, and so forth and so on. And the other nice thing is all the other fields will be initialized to null, so I can write this in a very terse format. That was something that I liked when I went back to C to look at some of this stuff. So what's the next level embedding that we can talk about? And the next level embedding, I think, is a very interesting extension of what we can do with Cython. So who here is not familiar with what Cython is or does? OK. So Cython is what you might call a Python transpiler, a compiler from Python to C code. So what you can do in Cython is you can take a Python module like this, and you can see this module has a single method in it called foo, and this method does exactly what we've been looking at in every single other example. It creates a value given a type, creates another value given a type, and it multiplies them together. And if I run this module, they are really having a lot of fun. If I run this module with the same arguments, you can see it gives me 100. If I run it with string, that. Pretty simple. What I can do with Cython is, and I'll show you in the makefile, I run Cython on this file, and I end up with a file called mod.c. Just the same name as the module, the Python file, but it's a C file, where what they've done is they've taken some of this process of this pure embedding, and they've done it automatically for you. They've done it in a computer-generated fashion, so you can see there's an enormous amount of information here that is very hard for a human to work through, but it's computer-generated, so it's fairly complete. And you can see that if we look in here, we'll find our pi number multiply somewhere here. So this guy right here is the function that we wrote that has been transpiled into C. And it is incredibly ugly C, because it's computer-generated. And you can see the decrefs that we had in our pure level embedding are here as well. And you can see the get adders is right there. But this is just an automatic transcompilation of our Python code to C code. Now what we can do with this is we can build it. We can build this into a Python shared object, an extension module, using the exact same things that we're familiar with. The only change here in the build step is that we want to build this as a shared object, and we want it to be position-independent code. Otherwise, for the most part, the GCC flags and the GCC command that we use to build this is pretty much the same. So let's take a look at this in use. Here's my Python interpreter, and I'm going to import mod. And one thing I'll show you is that this is going to use, so when you import things in Python, it has a default pathway, and it'll default to using the shared object over using the Python file. And I'll show you how you can prove that to yourself. You can see that the file that represents this module is the shared object, not the Python file that I wrote. And we know there's a foo in there, and we can see it taking our same arguments. Giving 200, and nothing up my sleeve, giving 10 repeated 20 times. So what could we do with this to create a new type of embedding? What if we go into this C file, and we notice that, so let's find pi number multiply, because we know that's the function that we actually compiled. This is our foo function. And we scroll up to the top. And if we scroll up to the top, I want to show you the before file. Oops. We scroll up to the top, we'll see that there is a qualifier on this function. It's a static qualifier. And if anybody here remembers what the static qualifier on a C function does, well, nobody here probably does, so I'll tell you. In C, there is no sense of namespaces, but there is the ability to protect visibility for a function so that it can't be seen outside of a module. What they've done here is they've transpiled my Python code into C code. And they don't want the actual pure C function to be visible outside of this module. So they've given it this static qualifier, so nobody else can use it. It's not an exported symbol. So if I were to link this shared object against another binary, that binary would not be able to call this function. What they want to do is they want to make it so that we can only call functions which they have made specifically visible to the Python interpreter. So if we go down later in this file, we'll see the same boilerplate around init module where it sets up a couple of methods and it tells the interpreter that here are the methods that are available and initialize these with a doc string and with the actual pointer to the actual C code that's run. What we can do is we can remove these static qualifiers. And I have done that. So I'll show you a diff between before and after. All I've done is I have removed the static qualifiers. The function prototype had a static qualifier, and I removed the static qualifier. The function itself had a static qualifier, and I removed it. So what can I do with this? Well, now I have a C shared object in which I can call directly into it, and I can call a function that's been transpiled from Python. So what I can do is I can create a main function, and this is now a pure C application. And what I can do is I can create a prototype for this guy, and I can call it directly right here. And for convenience, what I've done is I've taken inputs that were provided on argv, and I've converted them from C strings into Python strings. But one thing that I could think about is if I wanted to push this example further, I don't need to use pystring from string, because I know what a pystring looks like. I know what the struct looks like. So I could define that struct directly. I could just write out, initialize the struct to these fields, because I know exactly what the fields are. Well, here's another interesting thing. I don't need to use the Python garbage collector, because the Python garbage collector is only useful for automatically constructing the string. But this is my own C program, and I know how much memory, and I know what I need to create. So I could create these Python strings without using the Python garbage collector. In fact, I could do all these initialization steps in PyInitialize without using the Python interpreter itself. And so what you could think is I could take this example, and with enough time and effort, with a little bit of grind, what I could do is I could replace every case where it uses the standard interpreter, where it uses the facilities in the standard interpreter, and I could encode directly in my file only the pieces that I specifically need, such that I could be running Python code in a C program without the Python interpreter itself, without the garbage collector, and without anything that I don't need. And all it would require is for me to take this same process and to just repeat it, and to grind and to take out the pieces I want. This is why I ambitiously call this a zero interpreter embedding. It means that one very interesting thing that we can do is run Python code without the Python interpreter. We could, for example, run this on an embedded system, even if it were memory constrained, because we don't need the interpreter if we know exactly what objects we're creating. This is what I mean when I call Python a system within a system. Because what is the difference between me creating a stripped down version of the interpreter in my own C program and using the interpreter itself? Well, I've gotten rid of a lot of conveniences, and I can no longer run custom code. But for this case, I already know the code that I want to run. It's a function that I've already written. I'm not just running arbitrary scripts. And in most of our systems, we aren't running arbitrary scripts. We're running a set of static code that we know, that's been written. We're not accepting random user code to run dynamically. We're only running developer code that we've already written and tested and pushed to a particular branch in our deployment system. What this means is that we shouldn't think of Python as this opaque entity, this interpreter that just kind of goes off and does some magic to run our code. What we should think of is Python is just a gradation from one system to another system to another system, and that we can we can write code, and where that code runs, or having that code run within the standard interpreter is merely a convenience of wanting to use the features that the standard interpreter gives us. But it's not a necessary quality. If we want to really get to the meaning of what Python is, we can say it's merely just another application that runs on my computer. And it's an application that if I wanted to, I could modify or I could embed in a different way. And the distinction between my code and Python code and even the OS code can be blurred, such that people say that Python is not very well suited to embedding on a device with not a lot of processor speed, without a lot of memory. And you can say, yes, that's correct, if you're using the standard interpreter. But we can see from this example that perhaps we don't need to think strictly in terms of there is just a standard interpreter. Perhaps we can blur the distinction between what is the standard interpreter and what is maybe a more specified, more concretized view of Python. We could, for example, use these kind of embeddings in order to make use of Python in areas where we aren't necessarily using it through the standard interpreter. So I think it's a very interesting conceptualization of Python. But we can take this a little bit further. So, oops. Let's take this a little bit further to C and exported symbols. So one thing that we may be interested in thinking about is this very high-level embedding and extension modules. And before we look at that, I want to talk very briefly about the C compilation model. The C compilation model tends to be very primitive. One very nice thing about using Python is how many conveniences it gives us in terms of, or how primitive languages that we've used previously really are. When we compile a shared object in C, it exports a certain number of names. And those names, and we link a bunch of shared objects to another C binary. What it does is it determines which function to call when you say PyNumberMultiply based on the name itself. And there is no namespacing. There's no way for us to say that we need to use this PyNumberMultiply as opposed to this PyNumberMultiply. So for example, if different shared objects define functions with the same name, the linker has no way to distinguish which one you want to use. We run into some problems. We can see the exported symbols for a shared object or for a shared object using object dump. And I'll show you that for Modessa. So you can see these are all the exported symbols. And if we were to link this against something and one of the exported symbols were used, the interpreter would make your linker have no ability to determine whether or not, and I'll show you one of the ones that it defines, which is PyFoo all the way at the top. Where's the one that it defines? This is the, yeah. So this is these are some of the ones it defines. This is the one it defines here, PyPF3modFoo. It's going to determine which actual code to call directly based off the name. What this means is that if we were to create an extension module that itself started up a Python interpreter, we run into trouble. Because a Python interpreter has all the same symbols that the interpreter in which it's running will have. And so we'll run into a little bit of difficulty because we won't be able to disambiguate between which symbols reference the interpreter that is running the code, which one is referencing the host interpreter, and which one is referencing the guest interpreter. Or to put it another way, if I wrote this, Py3so test. If I wrote this embedding. So, this guy. So, this is actually a very interesting extension module. And this extension module contains only a single function, and that function is called eval. And what that function does is it calls pyrunSimpleString and runs some code within the Python 3 interpreter. And if I try and build this and link this against, and I try and import it, I'm going to run into trouble. Because pyrunSimpleString is a symbol that already exists in the host interpreter. But what I can do is I can use object dump or a number of other tools and determine what are the exported files in a shared object that represents the Python 3 interpreter. I can rename those by means of some source code transformation. What I can do is I can create a Python module that embeds a Python interpreter. So I'll show you that, and I think that's very, very neat. So let's take a look at Py3so2 is what I like to call it. So I need to export LD library path. I need to do a little bit of system setup just to get it to work correctly. And then let me source. We'll run Python. So here's my Python interpreter. And I'm going to import this module that I created, Python 3. And I have a eval in here. And it's just like the regular eval in that it evaluates code. So it evaluates 1 plus 1. Doesn't print anything out. So let's just print out hello world. But there's something very interesting that's happening here. I'm running Python 2 on the outside. I'm running Python 3 on the inside. I'm running Python 2 and Python 3 simultaneously within the same program, and they're within the same process space. I'm not shelling out. I'm not going off to another process. I'm not using multiprocessing. I'm running Python 2 and Python 3 simultaneously within the same process. And I'm going to show you that there's no tricks up my sleeve. This is actually the same process. And I'll do it using os.getPid, just to show you there's no trickery to this. I actually have two simultaneously running interpreters within the same C application. So let's take a look from os, import getPid, and we'll print getPid. So the internal interpreter says that its process ID is 2046, and the external interpreter says that its process ID is 20,046. So you can see we have Python 3 running from within Python 2. Now, one thing that I've wanted to do. Well, I really wish that I've really been meaning to get to this and to enhance this for future talks, because one very good point that somebody brought up to me is that I'm doing this the wrong way. Everybody should be using Python 3 these days, so I should be embedding Python 2 and Python 3. And if I'm going so far as to embed Python 2 into Python 3, what I really need to do is embed Python 1 into Python 2 into Python 3. But it turns out that it's actually very tedious to do the source code transformations. But you can see we have something very interesting here. And we might wonder, where is this useful, or what might we do with this? Well, I think it actually may be useful to have Python 2 running within Python 3. What that means is we may have a large Python 3 application, and by means of some import hook, we could say, when you try and import this file over here, run it using the Python 2 interpreter, because we know that module is not Python 3 compatible. And we may be able to have, within the same process, within the same memory space, two interpreters running simultaneous, where one uses one version of Python and the other uses another version of Python. And we could think that in some extreme circumstances, this may actually be a very valid use case to, for example, very softly migrate us from one version of Python to another, or to allow us to use two interpreters simultaneously in order to get around some bug, or in order to help us in some transition from one interpreter to another. Also, it's really cool. It's kind of like, I feel like Exhibit, and this is Pimp My Ride, and I've got a Python 3 running within your Python 2. I think this is really neat, and it's actually really fun. There are some things that make this not quite feature complete, however. The next steps from here are, you can notice that I have this function eval. So I don't really have the ability to interact with the code that comes out. And to interact with the code in the Python 3 interpreter is actually fairly easy. If you look at embeddings of other languages within Python, so there is a Lua embedding of Lua into Python, where you can run. They're very excited about this, I can tell. Right after this talk, I'm going to go next door, and I'm going to share this with them. Yeah. So if you look at the Lua embedding into Python, you can see what it does is it creates these shims, where all the Lua objects are shimmed by a Python object, and all Python objects are shimmed by a Lua object. So you can interact with objects across the interpreters. This is very easy to do for Python 2 to Python 3, because the objects tend to look very similar, and you just need to map a get-attr call in Python 3 to a get-attr call in Python 2. Very simple, very straightforward. The problem is when you look at things like the garbage collector and the global interpreter lock. If you were to create an object in Python 3, pull it into your Python 2 interpreter, and you were to create a circular reference, the Python 2 interpreter can figure out what happens if there's a circular reference within Python 2. The Python 3 interpreter can figure out a circular reference in Python 3. But they won't be able to see that there's a reference between the two of them. They'll have strong references going between the two interpreters, and it'll never get garbage collected. So the necessary step to fix that is to create some hybridized garbage collector that just looks into both lists of objects and figures out if there's references cycling between the two of them and cleans them up. That's a fairly straightforward thing to do. The really tricky thing is, what if you have a multi-threaded application running in the guest interpreter? How do you deal with the global interpreter lock? Because you could think that guest interpreter may be running code that needs to lock on an object. Oh yeah, I like this. I feel very excited. I feel more appreciated by them than some of the guys here. But you can see that the global interpreter lock is going to be another problem. So what you may need to do is in your shims, you may need to do some very coarse-grained locking just to make sure that you don't end up trying to mutate objects across the boundary. So that is an example of different embeddings that we can have with Python. So I showed you the very high-level embedding when you just use simple string to run code from within a C program. I showed you the pure embedding where you take all of these C functions like PyNumber multiply, PyNumber add, PyObject call object, and so forth and so on, and you just write them straight into a C program, and you're able to interact with them from your C program. I showed you a way you can use Cython to create a C shared object, which you can then link against directly from a pure C program, and which, given enough time, you could create a zero interpreter embedding. And then I showed you, I don't know if there's a name for this, but I showed you Py3SO2, an embedding of one interpreter to another as an extension module. Any questions? Turtles, because it is turtles all the way down. Any questions? I think this is really cool stuff. I don't know if it could ever be. I don't know if the more speculative pieces like the Python 3 or Python 2 may actually be productive for real-world tasks. But I know that for certain, the higher-level embeddings are something that I see all the time. So if you're familiar with Python.net, Python.net is a pure embedding of, I can't remember if it's a very high level or pure embedding. I think it's a pure embedding of Python into a .NET application, which allows you to access .NET libraries from Python. And I've seen this used at very large organizations in order to be able to write Python and to run it on Windows machines and have access to the C# GUI tools, DevKit and DevExpress or whatever they're called, DevGrid, and to actually have .NET GUIs with Python code running behind the scenes. I've seen this in real use. Additionally, if you, for example, had some program and you wanted to be able to add debugger and you want to be able to script that debugger in Python, or you want to just add scripting in Python, you can see that the pure embedding might be one way to do that. So I saw a trading system once, and they wanted to be able to very quickly create financial products, which didn't have to go through the full testing of what you'd have to do if you wrote it in C++, because they were only being traded in very small lots. So you didn't have to worry about things like memory efficiency or performance. And what they do is they'd sketch them out in Python, and they embedded into their trading system the ability to run Python code for these deal objects. And they did this using Boost Python, which is something fairly similar to the pure embedding. Any questions? Did anyone think this is kind of neat? Very good. Okay.